Hello, welcome back to Algebra. We're finally going to put to good use all of the properties of multiplying and dividing radicals and exponents of radicals that we learned in the last lesson as we simplify radicals that involve multiplication and division. This is part one. There's many parts to it because I want to give you a really great solid foundation and good easy problems to get your skills and confidence, good medium problems, and then some difficult problems toward the end. So we have a lot of problems here. By far, the most important rule that I presented four different kind of like rules in the last lesson. You should have watched that already. But by far the most important one is, or the most important two are the following. If you have something like two radicals multiplied together and they're the same order of the radical, like square roots, square root of 3 times square root of 5, you combine them underneath a common radical and you multiply what was under those radicals. That's rule number one. Rule number two is if you have a radical on the top of a fraction and a radical on the bottom, like square root of 2 over square root of 3, then I can combine that under a common radical again and make it 2/3 underneath the division of those two things. So those are basically the same rule, really. One involves multiplying things, one involves dividing things. That's by far the two most important rules of simplifying these that we can do. So let's go ahead and get started. We're going to start with some baby problems first, just to kind of refresh our memory and kind of get going, but quickly we'll ramp up into the interesting problems. What if I have the square root of 52? How do I solve that? What's the process? Well, the process is I try to write a factor tree. I go over here and I say I have the number 52, and I try to write what times what will give me 52, and I can pick anything. Now I know that it's divisible by 2, and I know that 2 times 25 is 50, so I know that 26 times 2 is 52. I can't go any farther with the 2 because it's already prime. The 26, I should remember, can be written as 13 times 2. And again, 13 is prime. I can't do anything other than 1 times 13. So I'm done, essentially, at this point. And then I look for pairs because it's a square root, not a cube root. And I see a pair of 2's in the bottom of my factor tree. So then at the end of the day, what I do is I take only one of those 2's. It only counts one time. I pull it out as a single 2, but this 13 is left all by himself. He has no pair. So he has to stay under the radical, the same order of the radical that I started my problem with. So the answer to this is 2 times the square root of 13. And a lot of you might not like that because the answer has a square root in it. Well, that's just tough. You just have to get used to that. Sometimes when the radicals don't simplify down to whole numbers, you're just going to have radicals in the answer. It's kind of like when you add fractions. Sometimes you get the answer as being, 1/18. Not a nice number, but sometimes the answer is 1/18. Sometimes the answer is 2 times the square root of 13. And this is a number. This just happens to be not a whole number. When you actually evaluate it in a calculator, it'll come out to some decimal. But whatever it is going to be multiplied by 2. And that'll be the final answer. All right, so let's move along here. If I had another problem where I had the square root of 162, and I was going to take the square root of that, what would I do? I would try to write a factor tree. I'd go right under here, and I know that this is divisible by 2, so I might grab a calculator to help me with that part, and realize that 2 times 81, in other words, just take the 162 divided by 2, and you'll see the answer is 81. So you know that these multiply to give me this. 81 is beautiful because you know that 9 times 9 is 81. Now I could go down and make this 3 times 3 and 3 times 3, but I don't need to because in the process of this, all I'm trying to do is look for pairs. Once I see a pair, I can circle that pair. I can pull out that single 9 because it only counts one time for each pair here. And then the 2 is an orphan. He has nobody to partner with, so he stays under the radical. The answer to that is 9 times the square root of 2. So you see these problems are not difficult. And we're going to quickly get into the problems that involve the properties that we're dealing with. But before we do that, let's say we have 196, and we're going to take the square root of that. What do? Same story. We try to figure out what can we multiply to give me 196. I don't know exactly, but I know it's divisible by 2, so I grab the calculator and I find out that 2 times 98 is actually what is equal to 196. And then I divide this by 2, and I figure out that 2 times 49 is equal to 98. Now 49 is a perfect square. I know right away that 7 times 7 is 49. And I'm looking for pairs. I have prime numbers in the bottom. I can't really go any farther with my tree. But I see that I have a pair here, and I have a pair of 2's here. So the 2 comes out as 1 unit of 2. And the 7 only counts once as well, and they get multiplied together, so the answer to this is 14. Now this is actually, turns out to be a perfect square. 14 times itself, 14 times 14 actually is exactly equal to 196. Now so far these problems have just been getting the blood flowing and getting you thinking about radicals again, right? But here in the next problem, we're going to have our first problem where we actually have to use one of the properties. So what if we have 8/9, and that whole thing is under a radical? If you didn't know the properties of radicals, it would be difficult to know what to do, because even if you try to use a factor tree here, yeah, 9 has a perfect square, 3 times 3, but 8 is not a perfect square. You can't say that 8 is like 2 times 2 or something, because it's 4, right? 8 is not a perfect square. So the only way to proceed here is to break up that fraction. Also, I told you in the last lesson, when we simplify radical expressions, what we're trying to really do is we're trying to break all the radicals up such that we have two things happen. No fractions underneath the radical. So we don't want any fractions underneath any of the radicals. And the second thing is we don't want any radicals in the denominator of a fraction. So just to kind of reiterate that one more time, I mentioned it in the last lesson. We don't want anything like 1/5 underneath a radical. That's a fraction under a radical. We want to fix that, break it apart. And we also don't want anything like 2 over the square root of 3. We don't want any radicals in the bottom of a fraction. We don't want that. I'm going to teach you how to get rid of those as we go on. We don't want either of these cases. And of course, we want all of the radicals evaluated. So what would this be equal to? We learned from the last lesson that this is going to be broken up into the square root of 8 over the square root of 9. That's really all you have to know. When you have a fraction under a radical, break it up. It's the same order of the radical. It's a square root on the top, square root on the bottom. If this were a cube root, it would be cube root of 8, cube root of 9. You see, if it was a fifth root, it would be fifth root of 8, fifth root of 9. So now I have two problems to solve. So I try to do the first one first. The square root of 8. What happens here? Factor tree. 2 times 4 is 8, all right? And then 4 is 2 times 2, and I'm done with that factor tree. So I have a pair, but I have an orphan. So the 2 comes out only one time, and this 2 does not have a partner, so he stays under the radical. It's not pretty, but that's what it is. And you already know that 9, the square root of 9, is 3. I don't even need to do a factor tree for that. It's 3 times 3, and you just circle the thing. So what we really have here, to continue on with our problem here, is the square root of 8 turns out to be equivalent to 2 times the square root of 2. The bottom is the square root of 9, which is 3. And so we've simplified this to its basically simplest form. And it doesn't look simple. I mean, a lot of you might look at this and say, this is simpler. But when we simplify radicals, what we're trying to do is eliminate all fractions under a radical, which is what we did. We don't have any fractions under any radicals. And we're also trying to eliminate any radicals in the denominator, like the square root of 9. In this case, it just went away because when we evaluate it, it goes away. So therefore, it is simplified. All right? Now let's crank through it here. We've gotten through the preliminaries. And now we'll really roll up our sleeves and slowly increase the complexity of these problems as we go. What if we have 4/3? That's a fraction. And let's say we're taking the square root of it. How do we handle it? We don't like fractions under radicals, so we have to break it up. We have a fraction under a radical. We just take the radical of the top and divide it by the radical of the bottom. Again, this is a square root, so these are square roots, but if this was a fifth root or a fourth root, these would be fifth roots or fourth roots appropriately. Now you know what the square root of 4 is. That's easy. It's 2. And square root of 3 is right here on the bottom. So you might say this is the answer, but again, that violates the second thing. I don't want any radicals in the bottom or in the denominator of fractions, right? It's more of a convention in mathematics more than anything. It goes back to the history of how square roots were calculated a long time ago before computers. And it just so happens that we don't want any radicals in the bottom for historical reasons. And that is what you're going to be graded on. So whether or not you like it is tough. You're just going to have to get rid of radicals in the bottom. This is the right answer. 2 over the square root of 3. That is a number and it is the correct answer, but we just don't want a radical in the bottom. So there's a mathematical trick. It's not really a trick, but it's a procedure to get rid of radicals in the bottom. And I'm going to write that out for you. When we want to kill this radical in the bottom, it's called rationalizing. Rationalizing the denominator. Let me show you what it is. It's actually very cool, very simple too. What we want to fix here, so to speak, is 2 over the square root of 3. Now remember, this is a fraction. Any fraction, even if it has a square root in it, can be multiplied or divided by anything you want as long as you do it to the top and the bottom. For instance, I can multiply this by 2 on the top and 2 on the bottom. It would still be the same fraction. I can multiply this fraction by 16 on the top and 16 on the bottom, and it would still be the same fraction. It would look different, but it would be the same thing. I could also multiply by decimals if I wanted to, but I could also multiply by radicals. I could, because a radical is just a number also. So I can multiply the top by the square root of 2, and I can multiply the bottom by the square root of 2. Essentially, when you multiply a fraction by something over something, as long as it's the same thing, you're just multiplying by 1. So whether you multiply by 5 over 5, that's multiplying by 1. Or I can multiply by square root of 10 over square root of 10. You're still multiplying by 1 because, anything over itself is 1. So what we're going to do is very carefully choose what to multiply here. We're going to multiply this by the square root of 3 over the square root of 3. What we're doing is we're multiplying by 1 because that's all it is. But what's going to happen here is we're going to kill this radical in the bottom in the process. So we multiply the numerators, which will give you 2 times the square root of 3. And then we have to multiply these denominators, but remember the rule. What is the rule with multiplying radicals? Right? That's the other rule that we learned in the last section. You multiply radicals as long as they have the same order, like they're both square roots or both cube roots. You bring them under a common radical, but you just multiply the numbers. So what you have here is 3 times 3. I know that that's 9, but I'm going to write it as 3 squared, and I'm going to take the square root of it. What you do is you combine them under a common radical and you multiply them. That's how you collect things. That's exactly the property we learned in the last lesson. But you know that this is 9 and the square root of 9 is 3, but another way to look at it is the square root cancels with the square, leaving only a 3 in the bottom. And on the top, you still have 2 times the square root of 3. Now, even though you may not agree, this is actually the preferred answer. It actually looks more complicated than this one, but these two numbers here, 2 divided by the square root of 3, is exactly equivalent to 2 times the square root of 3 divided by the number 3. If you get a calculator and do this, and you get a calculator and do this and divide, you will get the same decimal answer. They're the same thing. But by mathematical convention, we don't want any any fractions under a radical, and we do not want any radicals in the denominator of fractions. If we ever see a denominator that has a radical in it, we want to get rid of it. This process of multiplying by this is called rationalizing the denominator, right? So what you do is if you see a square root, you just multiply by that square root on the top and bottom, and every time you do that, because you're just multiplying the insides, you will always get a perfect square. Like if it were square root of 4 here, then I would multiply by square root of 4 divided by square root of 4. But then that would be the square root of 4 times 4, which you all know is 16, which is a perfect square. I would take the square root of that, I would get 4. So anytime you multiply a radical times itself, you're always going to get rid of the radical because what's going to be inside will be a perfect square, and then you can take the square root of it. So it's a quick and easy way to kill radicals, basically, and we always want to do that. Now, when we have, if this were the cube root of 3 or the fourth root of 3, I have to teach you a slightly modified, I should say, way to rationalize. But 99.99% of the time, it's just going to be a square root. And if it's a square root, you just multiply top and bottom by whatever you see here. And you should just get a number back. If you don't get a number back, you've done something wrong. All right, so that's called rationalizing. Now that we've gotten that out of the way, let's do another problem. Then we're going to have another opportunity to do this. Let's say the problem that you're given is 4 over the square root of 2. Simplify it. Well, we have a radical in the bottom. We don't want that. So what we're going to do is we're going to say this is equivalent to 4 divided by the square root of 2. But we're going to multiply this by 1, the number 1. But we're going to write the number 1 as the square root of 2 over the square root of 2 because this is 1, okay? And we know that when we multiply these bottoms, what we're going to get is the square root of 2 squared. We all know it's 4, but I'm writing it as 2 squared because it's easy to see that the square root will cancel with the square. On the top, it's 4 times the square root of 2. You can't really combine these anymore, easily anyway. And so on the bottom, you're going to have a cancellation. The square root and the square is going to cancel, or you can think of it as square root of 4. Either way, you're going to get a 2 on the bottom, and the 4 in the square root of 2 is going to be on the top. All right. Then what you're going to have is, let me rewrite it actually. Let me rewrite it down here. You're going to have 4 times the square root of 2 over 2. Now, you see you have a 4 on the top and a 2 on the bottom. These can be simplified as we always do. 2 divided by 2 is 1, and 4 divided by 2 is 2. So the final answer will be 2 times the square root of 2. 2 times the square root of 2. Let's see if I'm correct. Yeah, 2 times the square root of 2. That's the correct answer. So believe it or not, if we take 4 over the square root of 2, which was the initial problem statement, That's exactly equal to 2 times the square root of 2, which is also equal to 4 times the square root of 2 over 2. So there's lots of different ways to write it, but this is considered the most simplified form. We don't want radicals in the bottom. We want to simplify any numbers outside as we can with any expression, and so that's what we're doing. All right. All right, let's move on to the next board. We're going to have some radicals that involve some larger numbers here. And I do not want you to be scared of larger numbers. If you have, for instance, 270, and that's a square root, on the bottom you have the square root of 6. There's actually a couple of different ways to do this. You could, because it's a radical divided by a radical, you could write it as a single large radical and have 270 over 6. And then you could grab a calculator and take 270 divided by 6, and maybe it will come out to something, or you could just simplify that fraction that comes in there, and you could try to go from there. That's totally fine. You can do things different ways, guys. There's no one way to do it. But it's not the way I did it, and I'll show you the way I did it, and you can do it that way if you like, and you'll get exactly the same answer. What I did is, let's try to simplify the numerator and the denominator separately. 270, what would that be as a factor tree? Well, 270 can be written as 27 times 10, right? And 10 can, of course, be written as 2 times 5, and that's as far as I can go down there. But 27, I know, is 9 times 3. So it's 3 times 9 here. That's equal to 27. And the 9 can then finally be written as 3 times 3. And I'm looking for pairs because it's a square root. But I only have one pair. This 3 times 3, that's all I have. So this square root of 270, the single 3 comes out. And on the inside, I have to multiply everything left under the tree. So it's going to be 3 times 2 times 5. So it's going to be 3 times the square root of 3 times 2 is 6. 6 times 5 is 30. So 3 times the square root of 30 is what's in the numerator of this thing. All right? And then I go and say, well, what is the square root of 6? The square root of 6 is just 2 times 3. But this is not a pair at all, so there's no way to simplify this at all. So when you get down to it, you can say that this then is equal to the square root of 270 is 3 times the square root of 30. And on the bottom, you still have a square root of 6. Now, a lot of students would just circle that because you really can't do much more, right? You've already simplified the top, the bottom, there's nothing that can be done, so you think you're done. But then you go back to what I said before, we do not want anywhere a radical in the denominator of any fraction. And unfortunately, we have it here. So then how do we do that? We have to rationalize the denominator. We have to multiply that fraction, as ugly and as painful as it is, by the square root of 6 over the square root of 6. So let's do that down here below. You're going to have 3 times root 30 over root 6, and we're going to multiply by root 6 root 6. So on the bottom, what you're going to be able to combine these because they're multiplied, and you're going to have 6 times 6 is 36, but I'm going to write it as 6 squared, and I'm going to have the radical of that. And on the top, what am I going to have? I'm going to have the 3 out front. I'm going to have the square root. I have the square root of 30 times the square root of 6. I can combine those. 6 times 3 is 18, so it's going to be 180 in the numerator. It's going to be 3 times the square root of 180 because 30 times 6 is 180. Get combined under the common radical. This gets combined as multiplied under the common radical as well, right? So in order to really make any progress, you need to figure out what the square root of 180 is. So let's go over here and do 180. And it's nice because it's 18 times 10. I know that that's equal to 180. And I know that 10 is 2 times 5. I'm done with that side of the tree. And then 18 is 9 times 2 is 18. And 9 is 3 times 3. And again, I'm looking for pairs. So I see a single pair of 2's here and a single pair of 3's, right? So what I'm going to have is I'm going to pull out a 3 and I'm going to pull out a 2. So what I'm going to end up with here is 3 times 2 on the outside will be 6 times the square root of 5. Because the 5 is left over, it has to stay under the radical. 6 times the square root of 5. So what I'm going to have coming back to my problem is, don't forget I have a 3 outside of that radical. So that's going to be multiplied by whatever this is equal to, which we just found was 6 times the square root of 5. And on the bottom, it's the square root of 6 squared. They cancel the square and the square root, or you can think of it as the square root of 36. Either way, you're going to get 6. But look what you have. You have a 3 times 6, of course I could do 18, and then 18 divided by 6 is 3, but another way of looking at it is the 6 on the top cancels with the 6 on the bottom. And they're basically gone. You can multiply and divide if you'd like, but essentially it's going to be 3 times the square root of 5. And that's the final answer. It's a lot of work to get there. I mean, the whole entire board is just numbers, but it is not that hard to do, basically. Now, there are other ways to do this problem. You can, instead of simplifying the top and the bottom and rationalizing, you could combine these into a single radical, 270 divided by 6, and then you would have to simplify the fraction 270 over 6, and maybe try to make it simpler that way. And maybe it is much, much simpler to do it that way, but that's okay. I did it differently. You might do it differently on your paper. Either way, you should get 3 times the square root of 5. All right, either way. All right, we only have 2 more problems. We have plenty of room on the next board to do that, so let's move over here and do the last 2 problems. What if we have square root of 30 multiplied by the square root of 42? Okay, the first thing I'm going to try to do, I know that I can multiply and combine those together, but under a common radical, 30 times 42 is going to be a really big number. I'd really rather not deal with really big numbers. So rather than just multiply right away, the first thing you should check is try to simplify any one of these. Maybe you get lucky. So let's look at the square root of 30 first. Well, I know that 3 times 10 is 30, and I know that 10 is 2 times 5, and I can't go any farther down the tree, and I have no pair, so I can't really simplify the square root of 30. So I have over here the square root of 42. And I try that, and I say 7 times 6 is 42, and 6 is 2 times 3, and I can't go any farther with any of these, and I have no pairs. So as much as I wanted to, I have to check anyway. I cannot simplify either of those radicals. So I have no choice other than to combine them under a common radical, and 30 times 42 is going to be, let me just write it as 30 times 42, is going to be under a common radical, which is going to be a large number, 1260. And it's not nice to have such a big number, but it's just the way it is. So how do you handle it? I know it's an even number, right? So I just grab a calculator, and if you can't use a calculator, you have to do it by hand. I'm going to divide by 2, and it turns out that 2 times 630 is equal to this. I know that's even, so I'll divide that again. That's 2 times 315. Now this ends in a 5, so I know that I can divide that by 5. So 5 times 63 turns out to be right. And finally, I have low enough numbers. I know that 63 is 7 times 9 from my multiplication tables. And I know that 9 can be written as 3 times 3. So you go back up your tree, and everything here should be prime. And it is. So I look for pairs. I have a pair of 3s right here. And I have a pair of 2s way up in the top. I have a 5 and a 7. There's nothing else here. So what I have for the answer to this radical here is 2 times 3, so write it as 2 times 3, that's on the outside. 1 2 comes out, 1 3 comes out, they're multiplied. On the inside, I have 5 times 7, right? So what I have on the inside is 6 times the square root of 35. 6 times the square root of 35, that's the final answer. Just double checking myself. All right, final answer. All right, not too hard. A little tedious. Yes, you have to go down a couple of roads because you should always try, but ultimately, if you get a big number, you just have to deal with it. I mean, if you can't use a calculator, you're going to have to divide things and figure out what the factors are. Okay, what's our last problem? It's not too big, so I think I have enough room to kind of like carve out over here to do it. Last problem. Square root of 6 multiplied by 2/3, and I'll take the square root of that. All right, there's a couple of things that you could do. I'm going to discuss what they are. First thing you can try to do is simplify 6. The square root of 6. So I'm not going to do it, but if you were to do a factor tree, it's going to be 2 times 3. Those are already prime, there's no pairs, so you can't really simplify square root of 6. Then you look at this and say, well, it's a fraction, I'll break it up. I can make it square root of 2 divided by square root of 3. But if I do that, it doesn't help me that much because square root of 2 cannot be simplified anymore, and the square root of 3 cannot be simplified more either. If you try to do factor trees for either one of them, you're just going to get the same number. You're not going to get any pairs. So I really can't simplify them. So then I go back larger picture and I say I have a radical times a radical. So I have where I can bring them under a common radical, but I have to multiply what's here. Now this 6 is easier to see it if you write it as 6 over 1 times 2/3. All I'm doing is multiplying what's under the radical. So then what you have on the inside of this radical, you have a multiplication of two fractions. 6 times 2 is 12, and 1 times 3 is 3, and that whole thing is wrapped up under a radical. Nicely enough, 12 divided by 3 is 4, and you all know that the square root of 4 is 2. So the answer to this whole ugly problem is 2. Right? So that's the final answer. There's nothing else to do. But you know what? I want to do it a slightly different way to show you that there's always more than one way to do it. Let's do this one a slightly different way. It'll be fun to do something different. Square root of 6 times, I'll write the 2/3 first, and I'll write it as a square root. Now let's do it this way. We weren't able to simplify too much, so I didn't go down the road here, but you can write this as the square root of 6 times, this is a fraction. I can write it as the square root of 2 divided by the square root of 3. Now I didn't do it in this problem because I was thinking out loud that I couldn't simplify this any further, and I can't simplify this any further. That's true. But when you think about it, this square root of 6 can always be written over 1. It's a fraction. Anything can be written over 1. So I can actually multiply the tops and multiply the bottoms of these two things. When I multiply the tops, I'm going to get the square root of 12 because I just multiply what's on the inside, I bring them under a common radical. On the bottom, I'm going to have the square root of 3. All right? So then I go over here and say, what is the square root of 12? So let's go and see what the square root of 12 is. Well, 12 is 2 times 6, and 6 is 2 times 3. I have a single pair, which is right here. So I pull that number 2 out, and I have a square root of 3 left over. So the square root of 12 actually turns out to be 2 times the square root of 3, and on the bottom you have a square root of 3. Now I was just going to get ready to kill that denominator with rationalizing it, but here radicals can cancel just like any number. I mean, the square root of 3 is just a number, and I have the exact same number on the bottom. So all I have left is the number 2, which is exactly what I got before. So you see, you might go this way, you might go that way, but as long as you're following the exact same rules, you will always get to the correct answer. So here we've done simplifying radicals using multiplication and division. And the biggest picture that you need to understand is that if you have two radicals multiplied together, you can combine them by multiplying what's under those radicals under a common radical. Or if you have two radicals divided by one another, you can combine them under a common radical, and then you have to divide, what was underneath the original radical. So basically you can break them up and put them back together again, like Legos or something, but you just have to be careful that all of these radicals have to have the same order. Like they all have to be square roots, or they all have to be cube roots, and so on. Now in this lesson, we've done almost exclusively with square roots to get you comfortable. And as we go on, we'll be doing the same rules with cube roots and fourth roots, and you'll see some gotchas along the way. So follow me on to the next lesson and get more practice with simplifying these radical expressions.